In this lecture, we'll look at the zeroth law of thermodynamics. In the previous lectures, we have discussed briefly that there's a need for introducing laws of thermodynamics in classical thermodynamics because these laws introduce additional variables or properties that are not known outside the domain of thermodynamics. So, in this lecture, we'll begin with the zeroth law of thermodynamics. Now, why is it called the zeroth law? So, this law or postulate was established by Fowler in 1931, and that was much later than the other three laws, the first, second, and third laws of thermodynamics. So, to avoid disturbing the traditional convention of numbering those first, second, and third laws of thermodynamics, the new law that was by Fowler was named as the zeroth law of thermodynamics. Now let's look at what does this zeroth law of thermodynamics states. So the zeroth law of thermodynamics states that if two systems are in thermal equilibrium with a third system, then they are also in thermal equilibrium with each other. In other words, if you have three systems, let's say A, B, and C, what this law says, or what this statement of the zeroth law says, that if A is in thermal equilibrium with C and B, system B, is in thermal equilibrium with system C, then A and B are in thermal equilibrium. So this is what this law states. Now note that this law deals with thermal equilibrium, not thermodynamic equilibrium. And we've seen that for thermodynamic equilibrium, we need equilibrium of all forms such as thermal, mechanical, chemical, electrical, or any other phenomena that goes on. But the zeroth law is applicable for thermal equilibrium. For example, if you have, let's say, chemical equilibrium, if you consider chemical equilibrium, and let's say you have systems A, B, and C. So let's say if A is composed of ammonia, B is composed of hydrogen chloride, HCl, and C is composed of nitrogen, then A and C and B and C, that is ammonia and nitrogen and hydrogen chloride and nitrogen, can be brought into equilibrium with each other. However, if we have A and B together, then they will react rapidly with each other. So that's why they will not be in chemical equilibrium. So that's why when we talk of the zeroth law, we'll talk only in terms of thermal equilibrium and not thermodynamic equilibrium. Now, if you look at a statement like this, essentially we can say that the zeroth law is the statement of transitivity of thermal equilibrium, because if A and C are in thermal equilibrium and B and C are in thermal equilibrium, then the statement says that A and B are in thermal equilibrium. So it's like a transitivity relationship. Now, the importance of the zeroth law is that it provides us with an analytical criteria of thermal equilibrium. That means the zeroth law states that there is an equality of a certain property of systems That means there is an equality of a certain property of systems which are in thermal equilibrium with each other. And we'll see that this property is what we call as temperature. And temperature is what distinguishes thermodynamics from other branches of science. And note that temperature is not known in other branches of science, and thermodynamics introduces it as a state property or property of the state. Now let us see how the statement of the zeroth law is given over here, and a very simple statement suggests that there exists a property which we'll call as the temperature, and this property, that is temperature, must have the same value when a system is in thermal equilibrium with other system. So this statement itself, the statement of the Zeroth law itself, suggests the existence of temperature as a state property. So let's look at how we can use that statement to show the existence of temperature as the state property. So to this end, let's consider three systems. Again, let's say we have, let's say, systems A, B, and C. And these systems can exchange heat with each other through diathermal walls. Now each of these systems A, B, and C are characterized by a certain number of variables which we have defined earlier as the properties of the system. For example, we have seen for a homogeneous system of a pure substance of a given mass, only two intensive properties are required to unambiguously define the state of the system. So let us consider that these two variables or properties are, let's say, pressure and the specific volume. So by defining the pressure and specific volume, let's say for a given mass of gas, we can identify the state of that system. Now, if we have any of these two systems, let's say A and B, which interact thermally, then the properties of these two systems, A and B, or A or C, or B or C, are going to change when you have thermal equilibrium. So, for example, let's consider that there is thermal equilibrium between systems A and C. So when these two systems A and C are going to attain thermal equilibrium, they have these four properties: PA, VA, PB, and VB. They'll attain some new values because with these two values for every system will correspond to a different state of the system. So once they are in thermal equilibrium, the pressure and volume are going to change. That means upon thermal equilibrium, these values PA, VA, PB, VB would be related by some functional relationship, and this functional relationship, let's say, is given by some function f1, PA, VA, PB, VB equals to 0. In other words, the pressures and volumes of both these systems are interrelated when you have thermal equilibrium. So here f1 is some function which will depend upon the type of pure substance that you have. Now this equation can alternatively be written as, let's say we can separate out PC. So PC is some function which we don't know what that function is equal to PA, VA, VC, and we don't know this function f1 because we are just considering some general system which can be described using two properties. Similarly, if we have, let's say, B and C are in thermal equilibrium, then we can say that there is a relationship between their measurable properties, which are pressure and specific volume. So we'll have, let's say, F2. So we'll have a relationship between their observable properties, and that mathematical relationship is given by PB, VB, PC, VC. So a function of these variables would be 0. So there's an equation, and we can also alternatively write this equation as PC is some function of the other three variables, which are these. Now, from the Zeroth law, we know that if A and C are in thermal equilibrium and B and C are in thermal equilibrium, that implies that A and B are in thermal equilibrium. That means, first let's see what do we mean by A and B are in thermal equilibrium. So if A and B are in thermal equilibrium, that means we can again write a relation between their properties of state, and this will be, let's say, F3 is given by this F3, which is a function of PA, VA, PB and VB is equal to 0. That means there's a relationship between the pressures and volumes of systems A and B. Now the zeroth law says that if A and C are in thermal equilibrium and B and C are in thermal equilibrium, that implies A and B are in thermal equilibrium. So the statement that A and C are in thermal equilibrium is this, and the statement that the B and C are in thermal equilibrium mathematically is given by this. So from zeroth law we must be able to use this equation and this equation to arrive at this particular equation. That means we must have F1 from here is equal to F2, and this statement, the statement of the zeroth law says that is should be equivalent to this particular statement. So these two statements should be equivalent to each other. But note that this relation shown in red color depends upon the specific volume of system C, but we should not have that specific volume of C while describing the mathematical relationship between the properties of systems A and B when they are in thermal equilibrium. So it should not depend upon the specific volume of C. So this is possible only if we have these functions f1 and f2 of the form that if we equate these two functions, then Vc cancels out. In other words, we must have these functions of the form f1, which is function of PA, VA and Vc, is equal to, let's say, phi1 times phi1, which is a function of PA and VA, times some other function of Vc and plus some another function of Vc only. Similarly, F2 is where this zeta and eta are the same functions, but phi1 and phi2 are different functions. Now let's say if we have functions of this form, f1 and f2, and then we substitute them in this equation in red color, then clearly the dependence on Vc is going to cancel out. If you equate f1 and f2, then you will get phi1, which is a function of the properties of system A, is equal to the state properties of the system B. And similarly, you can show with the same argument that you will have some function phi 3 which will be equal to these when you have PC and Vc as the pressure and the specific volume. So we started with a very simple statement of zeroth law, and from that we have arrived at a conclusion that there must exist some functions phi1, phi2, phi3 of these two state properties of systems A, B and C, such that if we have thermal equilibrium, then these functions must attain the same value. So this function phi1 is in fact the temperature. So that means we have temperature of A is equal to temperature of B, and that is equal to temperature of C. And phi1 can be any other function also. So it can be in fact any function that is monotonic with temperature. So that means if a monotonic function is equal, then that means the temperature is also equal. So the zeroth law says that there exists a function of the variable properties of the system of the form t is equal to t of p comma v. So t can be, for example, phi in the previous equations. And this function t is such that if any two systems are in thermal equilibrium, then they are characterized by the same value of this function t, which depend upon the two properties which we have taken as p and v. In other words, the zeroth law asserts the existence of an equation of state of the form that there is some functional relationship between pressure, specific volume, and temperature. And from high school, you already know that what is the equation of state for a particular example of an ideal gas where P, V, and T are related. Now, as we have noted earlier, classical thermodynamics does not provide us with the exact nature of such equation of state. Therefore, one has to resort to either experimental data or theoretical considerations from microscopic viewpoint to arrive at such kind of equation of state. All we get from here is that there is some relationship that P, V, and T are connected. Now, if we in fact look back, what we have is that for thermal equilibrium between A and C, B and C, and A and B, we have three equations over here denoted by capital F1, F2, and F3 equal to 0. But what we have are six variables, that means pressure and specific volumes of systems A, B, and C. So the remaining three equations come from the equation of state, and that's why there must exist some functional relationship between the temperature and the pressure and the volume. So the zeroth law tells us that there exists a property that we call as the temperature, which is equal when two systems are in thermal equilibrium. And the zeroth law forms the basis of temperature measurement. What do we mean by temperature measurement? So temperature can be measured by any property that can be measured that changes when a system attains a new thermal equilibrium with another system. For example, in the previous analysis, we've seen that upon achieving thermal equilibrium, the pressure and the specific volume may change. Now, if you want to construct a simple thermometer, you may consider a gas enclosed in, let's say, a bulb of fixed volume. Then, whenever you bring this bulb filled with gas having dithermal walls in contact or in thermal contact with another system, then the volume is fixed in this case, but the pressure is going to change. And if we have means to measure that pressure change, then pressure can be used for temperature measurements. That means in this case we say that pressure is the thermometric property. And this property, or for example pressure as a thermometric property, is used in a thermometer which is called a gas thermometer. Similarly, you can measure temperature by having any different thermometric properties. For example, let's say you have this mercury in bulb thermometer, where you have this mercury filled in this bulb of a glass tube, and there is a bowl in which the level of mercury increases. So this length of the mercury column can be used to measure the temperature. So here the property that we are going to use is the volumetric expansion of mercury, which can be measured in terms of the length of the mercury column in this mercury in bulb thermometer. Similarly, you can use any other thermometric property to measure temperature. Another example is, let's say you can have a temperature dependent resistance, and typically that is for a platinum wire, and that is used in the RTD thermometer, the resistance temperature detector. Another type of thermometric property is that is used in thermocouples is that if you have two distinct materials, for example two different alloys, and their wires are joined or welded to form a junction, then the potential difference or the EMF that you measure at the ends of these wires will depend upon the temperature. So that property can also be used for temperature measurements. Any macroscopic quantity that you can measure and that is sensitive to attainment of new thermal equilibrium can be used as the thermometric property. Now, how does Zeroth law forms the basis of temperature measurement? So we've seen that Zeroth law says that if system A is in thermal equilibrium with C and B is in thermal equilibrium with C, that implies A is in thermal equilibrium with B. So imagine that you want to measure, let's say, temperature of, let's for example consider water in an insulated flask. So what you can do is you can consider this as your system A. Then what you can do is you can consider your mercury in bulb thermometer as system C, and system B can be some standard or reference system, for example any system which can be maintained at that particular state with quite an ease. Now what you do is, so this is my system B and the water in this thermos flask is my system A. So now this is how we use the Zeroth law for temperature measurement. So we dip our thermometer C in A so that they are in contact with each other. That means they can interact thermally. So what you will get is, when you do so, the thermometer will show certain length of the mercury column that you are going to measure. Similarly, if you bring your thermometer over here, again it is going to show some length of the mercury column. Now if these two lengths happen to be the same, then we'll say that A has the temperature that is equal to that of B. So this is how Zeroth law allows us to measure temperature. So what we do is that we fix the values of temperature of some references, and then from that we can say that if we define temperature of this standard reference with some, let's say, particular value x, then we'll say that the temperature of A is equal to x. So what are these standard references that one can use? So typically the standard systems are those whose states can be easily reproducible, and their reproducible states are called the fixed points. So two fixed points must be familiar to you. So one fixed point is called the ice point, that corresponds to ice water mixture at 1 atmosphere pressure, and another fixed point is the steam point that corresponds to the equilibrium between the liquid and vapor phases of water at 1 atmosphere. That means the equilibrium between liquid and steam at 1 atmosphere. So for Celsius scale, so you can define any different scale, but for Celsius scale, this is assigned a value of 0. So we'll say that this is 0 degree Celsius and this is at 100 degree Celsius. So in practice, you cannot have this reference state be at all values of temperature that one may anticipate. So you will have only few of these standard reference states, and if you get any different, let's say, length in between the lengths that come for correspond to these fixed points, then you can interpolate to find the temperature. So what one does is that, let's say, if you're using a mercury in a bulb thermometer, then let's say for ice point, if you get the length of the mercury column as L subscript ice, and for steam you get L subscript steam, and then for any length of the mercury column that you get by putting your thermometer in thermal contact with any other system, so this will be the length that will be measured when thermal equilibrium is attained. Then to interpret the temperature, you can use an equation for Celsius scale as 100 times L minus L ice over L steam minus L ice. So similar procedure you can use for different kind of thermometers which depend upon different thermometric properties. For example, resistance in an RTD or EMF in a thermocouple. Now this was the definition of Celsius scale that was used earlier. Later on this definition was changed, and now it is defined by fixing only one fixed point that corresponds to 0.01 degree Celsius, corresponding to the triple point of water, and the definition of the magnitude of 1 degree Celsius that is defined in terms of the ideal gas scale. Nevertheless, the ice point and steam point still are at 0 and 100 degrees Celsius. So similar procedure you can do for any different type of thermometer, and you can define different interpolation rules to interpret temperature. So here we've assumed that the volumetric expansion of the mercury behaves linearly with temperature. So that's why we can, let's say, divide this scale in equal gradations. But you might have a nonlinear relationship. Typically, for a resistance-based measurement of temperature, you may have a nonlinear relationship between the temperature and the resistance of the thermometer material. Now, what we've seen is that the zeroth law defines that there's something as temperature, a state property as temperature, but that temperature we are measuring in terms of other quantities. So the zeroth law does not provide us an absolute scale of temperature. So these scales that we've seen, you can define differently, but there exists an absolute scale of temperature that does not depend upon any thermometric substance, and that scale comes from the second law of thermodynamics. So the absolute scale is actually referred as the thermodynamic scale of temperature. And to understand that, we have to go to the second law of thermodynamics. But in practice, the thermodynamic scale of temperature is complicated to use, and in practice a different scale defined by a different standard called ITS, the International Temperature Scale, that was defined in 1990, so it is called ITS 90 standard, is used, which closely represents the thermodynamic scale. So thermodynamic scale is different and ITS scale is different, but ITS closely conforms to this thermodynamic scale, and that is more practical. So in this scale, the absolute scale related to the Celsius scale is called the Kelvin scale, and this is denoted by K. So these two scales, the Celsius and the Kelvin scale, are related by this relationship. So temperature in Kelvin is given by temperature in degrees Celsius plus 273.15, where 1 Kelvin is defined as 1 over 273.16 times the temperature of the triple point of water. So we will not discuss the details of this ITS 90 standard, but essentially what it does is that, similar to what we've defined over here in terms of ice point and steam point, the ITS 90 standard defines various fixed points and the rules to interpolate between these fixed points. And finally, note that this Kelvin scale is not the thermodynamic scale of temperature. It's a practical scale that closely conforms to the thermodynamic scale of temperature. But this thermodynamic scale of temperature is not what you get from the zeroth law. To get this, you have to go to the second law of thermodynamics. So what we've seen in this lecture is that the zeroth law is the statement of transitivity of thermal equilibrium and not thermodynamic equilibrium. And from the statement of the zeroth law, we arrive at a conclusion that there exists a property which we call as temperature, which must be same when two systems which are in thermal equilibrium with each other, and they both of those systems must have that same value of that property, which is the temperature. And the zeroth law allows us to measure temperature in terms of the variation in thermometric properties of different materials. For example, the length of the mercury column in the mercury in a bulb thermometer, or pressure of a gas in a fixed volume of bulb, let's say, or it can be resistance of a material which changes the temperature, or it may be the potential difference between the two ends of the wire which are connected by a junction which is maintained at different temperatures. So that is used in a thermocouple.